Hi, today we are going to talk about AVL tree. AVL tree is a binary search tree, but with a certain property. The property is that the difference between the height of the left, and height of the right is always 1, is maximum 1. It can be 0 or 1, but the difference cannot be more than 1 in the AVL tree. So we can say that AVL tree is kind of balanced tree. We don't have situation that all children in one side of the tree and the other side there is not much children. So for example, this tree is AVL tree because for every node the height of the left, in this case this is the height of the left, is 3. The height of the right, the height of the left is 2 here because we start from height 0, 1, 2. The height of the right is 1, 0, 1. So in this case it's AVL tree, and this applies to all nodes. For example, node 8, the height of the left is 1, the height of the right is 0. But this is not a AVL tree because for node example 12, the height of the left is 0, 1, 2, 3, while the height of the right is 2. So it's not balanced tree. So again, for node 8, the height of the left is 2, while the height of the right is 0. So the difference is 0. So the difference is 2, is more than 1. So in this case, this is not AVL tree. Why we care about AVL trees? Because if you remember the search and insert for binary search tree, how many operations we need for the search? In the worst case, imagine we want to insert, let's say 1. I have to compare 1 with 12 and then go to 8, 5, 4, 2, and then I insert the 1 here. So if this path is very long, then it's not efficient. In general, the worst case analysis, the insert is the number of operations I need in the worst case is the maximum height of the tree. So I'm trying to minimize the maximum height of the tree. Also in the search operation, in the worst case, I need the maximum height of the tree operations. So, but in some situation, if the tree is very bad like this, it's completely unbalanced. In this case, you need n comparison for the search and for the insert. So this efficiency here is n, which is not good. We are hoping to have a balanced tree. In the balanced tree, if the tree is like full binary tree or full balanced, then h is log n, which is very good compared to n. So in the AVL tree, we are trying to keep the binary tree balanced and to avoid such situation where we have very unbalanced tree, because in this case I need a lot of comparisons to insert or to search for a node in the worst case. So this is the idea of AVL tree. How can I make a AVL tree? It's like normal node. I define the node, I have data, I define something height because I need to check the height, and we have node left and right like before, and we have this constructor like the binary search tree. In the AVL tree class, we have a root node, and we can have a method called update height. So update height, because we will see in the AVL tree in some situation we are adding a node. After we add the node, we need to make the tree balance. So we need to update the height some situation. So the method update height is just change the height and make it correct. So n.height is equals to 1 plus math.max the height of the left and the height of the right. And here we just define the height method. If it's null, we return -1, else we return n.height. And we have a method called getBalance. So this getBalance is checking for node n if this node is balanced or not. How I know it's balanced or not? I compare the height of the right to the height of the left. If the difference, I want to see what's the difference between the right and the left. Usually in the AVL tree, the difference should not be more than 1 or less than -1. But I will use this getBalance in the rebalancing in the AVL tree, as we will see soon. So this is the AVL tree class, but we will add methods to this class. So the first method we will add is a helping method called rotateRight. In some situation, we have a tree like this. In this tree, we have like 3 nodes, y, x, and z. In some situation, we want to do rotateRight. What's meaning by rotateRight? I want to make x as the root, and I want to make y as the right side, and z I will make as a left side of y. Can I do this? Yes, because remember, this is a binary search tree, and because z is in the left part of the tree, so it's less than y. So I can make z as a left side of y, and z is greater than x, so I can make it in the right part. So when I make this operation, the binary search tree property is still the same, but I somehow, in some situation, I need to do this operation to keep it balanced. So we have a method called rotateRight. In this method, I give as input the node y. I define x to be y dot left. I define z to be x dot right. And that what I'm doing is that I say x dot right equal to y. So I will make y as x dot right, as you see, and I will make z as y dot left. So in this case, it's like I am changing this tree to this tree. And after this, I need to update the height of y. As we saw in the previous slide, we have a method update height and also update height for x, because now I changed the height of x and y. And then I return the root, the new root, which is x. So this is rotateRight. In the same situation, I can make rotate left. If I have a tree like this, then I make rotate left, then I will make x as the root. So in a similar situation, I defined x to be y dot right and z to be x dot left, and then x dot left will be y and y dot right will be z. In the same situation, I will update the height for y and x. I don't need to update the height for z because it's the same height like before. And then I return the new root, which is x. So I will use this operation in something called rebalancing. So rebalancing, after I insert a node in the tree, this insertion might make the tree not AVL tree. In this case, I have to make rebalancing. Rebalancing, I'm rebalancing some node and try to check the tree. If it's unbalanced, I need to make rotate left or rotate right, as we will see in details. So this is the rebalancing method. There are 4 cases. I will explain the 4 cases in details. So the first case, if the balance, so first here balance is the getBalance of z. I want to check if z getBalance, remember the method getBalance is the height of the right minus the height of the left. The first case, if the balance is greater than 1, means like the height of the right is more than 1 greater than the height of the left. In this case, we have this situation. So the height of the right is, in this situation, is 2. The height of the left is 0. So 2 minus 0 is greater than 1. In this case, I have such tree. But also I have height of z dot right is greater than height of z dot right dot left. So I have the situation where this part is greater than this part. So the height of this, the right of y is greater than the height of left of y. In this case, if I did z left operation rotation, then the tree will be balanced. So I will just do rotate left for z, and then I get a balanced tree from this tree. So this is the first case. Case 2, I have a different situation. I have the right has height more than the left, 2 times more than the left, the right, but the left part of y has height more than the right part. So in this case, I will do 2 operations. First, I will do right operation for node y. In this case, I will get x here, y here, and so on. And then I will get similar to the previous case. In this case, I will just do left rotation. Then I will get a balanced tree. So this is the case where I am doing. If I find that the balance is greater than 1, so the right part has more height than the left part, but the right is not greater than height right to left, so that's why we come in the else case. In this case, I will do rotate right for z, and then for z dot right, I will do rotate right for y, which is z dot right, and then I will do rotate left for z, and then I get balanced tree. The third case, if the balance is less than -1, so it's -2. In this case, the left part is greater than the right part. Okay, again, I have 2 situations. The first one is the left has more height than the left right. Okay, in this situation, it's enough to make right rotation for z. So if I did right rotation for z, it's balanced. The last case, again, I have the balance is less than -1, so the left part has more height than the right part. In this case, first I will do y left rotation, so I will do left rotation for the y, and then I get similar situation as case 3. In this case, I just do z right rotation. So first I do rotation left for z dot left, and then right rotation for z, and then I get balanced tree. So to summarize the rebalance is just a method, is trying to check if the tree is not AVL tree after the insertion, it will make some operation, rotate left or right, to make it a AVL tree and balanced tree. So first we update the height of the z, okay, and then we find the balance of the z, node z. If the balance is greater than 1, means like that the right part is the greatest part of the tree. Then we check another condition. If the right is greater than right left, then we do rotate left. Case 2, if it's not, then we do first rotate right and then rotate left. If the left part is the greatest part, then we check if left is greater than left right, then we do rotate right. Otherwise, we do rotate left and then rotate right as we saw before, and then we return the root node. Okay, so now insert is easy. It's just similar like the insert and binary search tree, exactly the same. Just we added, after we add the node, This addition maybe make the tree not AVL. So in this case, we do rebalance and return the tree node. And this is like helping method. Search is the same. We didn't change anything with the search. You can use it here, but now we guarantee that the tree we are searching is a balanced tree. So it's, in the worst case, it's big O of log n and not big O of n. So in the main class, we can use method insert, we add some nodes, we can easily search, and we can also use in order traversal to see that the nodes are sorted. So as exercise, we need to implement AVL tree as we saw before and test it. I hope it's clear, and talk to you in the next video.